In this presentation, we look at the end behavior of rational functions. Just as we did with polynomials, we can ask questions about the end behavior of rational functions. What happens for x values far away from 0, for large x values towards the ends of our graph, far from the y-axis? In many cases, this leads to questions about horizontal asymptotes and oblique asymptotes, sometimes called slant asymptotes. Before we go very far in discussing end behavior of rational functions, we need to agree on a basic fact. As long as a polynomial p of x has degree at least 1, so it's not a constant, then as x grows large, the polynomial p of x also grows large in absolute value. As x goes to infinity, 1 over the value p of x goes to 0. We explicitly list this as a lemma, that is, a mathematical fact that we will often use. Suppose that p of x is a polynomial of degree at least 1, then the rational function 1 divided by p of x tends to 0 as x gets large in absolute value. In calculus terms, the limit as x goes to infinity of 1 over p of x is 0. Here's a slight generalization of lemma 1. We'll call it lemma 2. Suppose that my rational function n of x over d of x has the property that the degree of the numerator n of x is smaller than the degree of the denominator. Then the rational function n of x over d of x tends to 0 as x gets large in absolute value. If the degree of the denominator is bigger than the degree of the numerator, then the highest power of x in the denominator begins to dominate as x gets very large, and the denominator begins to explode in relationship to the numerator, and so just as before, we end up getting something that's shrinking to 0. In calculus terms, the limit as x goes to infinity of n of x over d of x is 0 if the degree of the numerator is strictly smaller than the degree of the denominator. If my function is a rational function where the degree of the numerator is strictly smaller than the degree of the denominator, then this function tends to 0 as x gets large in absolute value. This means that if we have a rational function where the numerator has smaller degree than the denominator, then as x gets large, the graph approaches the x-axis. In other words, the x-axis, y equals 0, is a horizontal asymptote of the rational function. Here's how to find horizontal asymptotes of any rational function. Ask the question. Here's how to find y equals 0 as a horizontal asymptote. Ask the question, is the degree of the numerator smaller than the degree of the denominator? If it is, then y equals 0 is a horizontal asymptote. A corollary of a lemma is the result that follows directly from it. In this case, suppose we have a rational function where the degree of the numerator might not be smaller than that of the denominator. Divide the denominator into it using the division algorithm and write this fraction as q of x plus a new fraction r of x over d of x, where q of x is the quotient and r of x is the remainder. And by the division algorithm, we know that this remainder has degree smaller than that of d of x. Then the graph of f of x approaches the graph of q of x as x grows large in absolute value. The graph of my rational function will approach the graph of the quotient. Why is that true? It's because the degree of this remainder is less than the degree of the denominator d of x, and so that fraction r of x over d of x goes to 0 and begins to be irrelevant. We can write that this rational function n over d is approximated by this quotient as x gets large in absolute value. From the previous slide, this is important enough to repeat. If I have a rational function and I divide the divisor into the numerator and write it in this form, where q of x is the quotient and r of x is the remainder after division by d of x, then the rational function can be approximated by q of x in the large. The end behavior of the graph of the rational function is the graph of this quotient. Or, another way to say this, if we zoom out far enough, the graph of the rational function looks like the graph of this quotient polynomial. Horizontal asymptotes, some worked examples. Let's consider this rational function, x squared minus 9 over x cubed minus 4x. As we argued earlier, since the degree of the numerator 2 is smaller than the degree of the denominator, then y equals 0 is a horizontal asymptote. Let's take a moment to think about why that's true. As x is large in absolute value, maybe x is 1,000,000 or negative 1,000,000, then the denominator, which has x cubed in it, is much larger in absolute value than the numerator. And so this fraction begins to be close to 0. 1,000,000 cubed is about 1,000,000 times bigger than 1,000,000 squared. So the denominator dominates, and as x goes to infinity, or as x goes to minus infinity, my function approaches 0. Y equals 0 is a horizontal asymptote of this rational function because the degree of the numerator is smaller than the degree of the denominator. Suppose the degree of the numerator is the same as the degree of the denominator. Then the highest power terms dominate. The leading coefficients rule. For example, consider this rational function, which is a quadratic divided by a quadratic. As x gets large in absolute value, the terms x squared begin to dominate. 6x and 8x minus 12 begin to be irrelevant. For example, suppose x is 1,000,000. Then the denominator, x squared plus x minus 12, is equal to 1,000,000 squared plus 1,000,000 minus 12, which is slightly bigger than 1,000,000 squared. For all practical purposes, 1,000,000 squared plus 1,000,000 minus 12 can be approximated by 1,000,000 squared. In the same way, the numerator is equal to 1,000,000 squared minus 6,000,000 plus 8, which is this 12-digit number, which can also be approximated by 1,000,000 squared, or a trillion. So if I plug in 1,000,000 to this rational function, I get 1,000,000 squared minus 6,000,000 plus 8 on top, which is about 1,000,000 squared. I get 1,000,000 squared plus 1,000,000 minus 12 on the bottom, which is about 1,000,000 squared, and so this turns out to be just about 1. If I continue with this, the same result occurs if I set x equal to negative numbers, which are large, like x is a minus 1,000,000. More generally, as x is large in absolute value, this rational function begins to look like just x squared over x squared. Minus 6x plus 8 on top begins to disappear or become irrelevant. X minus 12 on the bottom, same thing. This begins to look like x squared over x squared, which is 1. So as x gets large in absolute value, my function approaches 1, and so the line y equals 1 is a horizontal asymptote of my function. Here's a graph of this function. With the function drawn in blue, the vertical asymptotes are drawn in red, and the horizontal asymptote is drawn in green. You can see how the function drawn in blue approaches the green and red lines in various regions. Let's look at this rational function. Like the earlier one, it has a horizontal asymptote at y equals 1, drawn in green, has a vertical asymptote drawn in red, and then it has a hole where x is 4. Here's another problem. Let's find the zeros and vertical asymptotes of this rational function and draw the sign diagram, and then find the horizontal asymptotes. Looking at the numerator, we see that the numerator is 0 when x is either minus 1 or 2. So those are the zeros of my rational function, since they are the zeros of the numerator. If I look at the denominator, I see that the denominator has zeros at minus 3 and 1. Since these are the zeros of the denominator, they are the vertical asymptotes of my rational function. Let's continue with this polynomial. Let's draw the sign diagram and find the horizontal asymptotes. If I take the zeros and vertical asymptotes from before, I had zeros minus 1 and 2, and vertical asymptotes minus 3 and 1. Put them in order, think of them as fences, try out some values in between the fences, and we'll get plus, minus, plus, minus, plus. There is one horizontal asymptote found by considering the end behavior. As x goes to infinity, this quadratic divided by quadratic approaches 3x squared over 4x squared. 3 is the leading term for the quadratic in the numerator. 4 is the leading coefficient for the quadratic in the denominator. Everything else disappears, and our rational function begins to look like 3x squared over 4x squared, which is just 3/4. So the horizontal asymptote is this line y equals 3/4. One more rational function, we saw this earlier. We could combine like terms and write it out as a cubic divided by a quadratic. If we do long division, take my word for it, we get this. So I can write that rational function, a cubic divided by a quadratic, as x minus 4 is the quotient, plus this remainder, minus 2x minus 7, divided by the denominator, x squared plus 5x plus 2. As x gets large in absolute value, that fraction, minus 2x minus 7 over x squared plus 5x plus 2, begins to disappear, begin to be very small, and so the rational function begins looking like x minus 4, which is a line. So the line y equals x minus 4 is an asymptote for this rational function where the numerator has degree 3 and the denominator has degree 2. In this case, this asymptote is neither vertical nor horizontal. It is a slant asymptote or an oblique asymptote. Summary. Asymptotes of a function are lines that approximate the rational function in the large as we zoom out and look at the global behavior of the rational function. Zoom out away from the origin and look at the behavior in the large, and you should see the asymptotes. Vertical asymptotes occur where the denominator is 0 and the numerator is not. If the degree of the numerator is less than the degree of the denominator, then there's a horizontal asymptote of y equals 0. If the degree of the numerator is equal to the degree of the denominator, then the rational function has a horizontal asymptote, which can be found either by doing long division or by focusing on the leading coefficients of the numerator and denominator. In an earlier example, the numerator had leading coefficient 3, the denominator had leading coefficient 4, so we got y equals 3/4. If the degree of the numerator of a rational function is 1 more than the degree of the denominator, then the rational function has an oblique asymptote, which can be found as the quotient after long division. Remember, asymptotes are lines. If you're asked for the asymptotes of a rational function, make sure to give an equation of a line. In the next presentation, we work through the 6 steps to graphing a rational function.